Hello, everyone. Welcome to my presentation, Predicting the Azimuth of in-situ horizontal stress by Integrating Multiple Discipline Data. My name is Bo Zhang from the University of Alabama. Here is the outline of my presentation. Let's first see why I'm interested in this topic, why my research is important. In a geologic sense, the main components of conventional reservoir include source rock, reservoir rock, and seal rock. A shear play is one where three rock components combine together. The hydrocarbon storage in rock pores does not flow laterally due to the low rock permeability. These figures illustrate the 48-stage shear plays. This bar illustrates the productions from different resources. We can notice that a significant amount of oil and gas come from shear resources plays. There are two goals in the shear resources characterization. The first goal is find the zones that are rich of TOC. The second goal is producing highway for the oil and gas flow. Due to the low permeability, it is necessary to enhance the recovery. The common enhanced recovery technology, such as hydraulic fracture. The hydraulic fracture can simulate fractures in the reservoir to extract the gas from the rock matrix and achieve a commercial gas production. The recent use horizontal drilling in conjunction with hydraulic fracturing has greatly expanded the ability of producers to recover natural gas and oil from low permeability geologic plays, particularly the shear plays. An efficient simulation creates new fractures and reopen or collecting pre-existing natural fractures. It is well known that the azimuth of horizontal stress are one of the main considerations in well planning and hydraulic fracturing. Let's see how we build the benchmark azimuth of in-situ maximum horizontal stress using microseismic data. This cartoon illustrates the hydraulic fracturing system. We have some pump trucks on the Earth's surface. The pump trucks on the Earth's surface inject high-pressure fluid to the reservoir to produce fractures. The producing of fractures will generate small earthquakes. We can use microseismic monitoring to observe the hydraulic fracturing. Microseismic monitoring is the passive observation of very small-scale earthquakes, which occur in the ground as a result of hydraulic fracturing. These blue, green, purple, red balls stand for the location of small-scale earthquakes, where we have hydraulically produced fractures. There are two factors that affect the growth of hydraulic fractures: the maximum horizontal stress and the paleo fractures. The hydraulic fractures usually grow parallel to the maximum horizontal stress when pre-existing lines of weakness are not present. However, if paleo fractures are present, this line of pre-existing weakness may serve as conduits for the fracture fluids, such that the paleo fracture serves as a position of subsequent microseismic ruptures. In this research, the effect of paleo fractures on the hydraulic fracturing is ignored. As a result, we can use the growth of the hydraulic fractures to indicate the azimuth of maximum horizontal stress. The trend of microseismic events can be treated as the propagation direction of hydraulic fractures. In this research, we compute the azimuth of the maximum in-situ stress by linear fitting the trend of microseismic ruptures. In this figure, the red dots stand for the microseismic ruptures. This black curve stands for the fitted line by using the location of the ruptures. The slope of the fitted line is used to compute the azimuth of local stress. Here is the first example of computing the azimuth of maximum in-situ horizontal stress using ruptures. The lines in the left figure show the variable trajectory. The color bars stand for the microseismic fracturing ruptures. The bars with the same color stand for the fracturing ruptures that were generated in the same fracturing phase. The right figure shows the roomed display of red ruptures in the left figures, nearby the well H1. According to the cloud of ruptures, we can compute the azimuth of the maximum local horizontal stress. Here is another example about computing the azimuth of in-situ maximum horizontal stress using the fracturing ruptures for one fracturing phase near well H3 locations. The figures on the right is a roomed display of the red ruptures shown in the left figures. In this example, we have 3 clouds of ruptures. As a result, we can compute the corresponding 3 azimuths of local maximum horizontal stress. Here is one more example about computing the azimuth of in-situ maximum horizontal stress using the fracturing ruptures for one fracturing phase near the well H5 location. The figures on the right is a roomed display about the red fractures shown in the left figure. In this example, we have 5 clouds of ruptures. We computed 5 azimuths of in-situ maximum horizontal stress. In this research, the azimuth computed from microseismic ruptures function as a benchmark for the following azimuth calibration. After I obtained the benchmark azimuth of in-situ horizontal stress, the next step is computing azimuth of anisotropy of seismic attributes. Here is one representative OVT gather. The wide seismic data is sorted into 9 different azimuths. This strong positive seismic reflection indicates the base of the target formation. Below the target formation is a carbonated formation. The first step in seismic anisotropic analysis is extracting proper seismic attributes, variation with offset at the target formation. In this slide, I show the seismic amplitude variation with offset for the base of the target formation at different azimuth spins. It is very obvious that different azimuths have totally different amplitude variation with offset. This is because the anisotropy. We employ the common procedures of computing the anisotropy ellipsoid. First, we will linear fit the seismic attributes variation with offset at different azimuths. When refitting or linear fitting is employed, we can obtain the intercept and the gradient of the linear curve. After I obtained the gradient for different azimuths, next I'm going to using an ellipsoid to fit the gradient. Then I can obtain the azimuth of the ellipsoid. Scientists has conducted extensive research about the seismic attributes variation with offset and azimuth. In this research, we compared seismic root mean square amplitude variation with offset and azimuth. We compared seismic maximum amplitude variation with offset and azimuth. We compared seismic amplitudes variation with offset and azimuth. We compared seismic dominant frequency variation with offset and azimuth. We compared instantaneous amplitudes and instantaneous frequency variation with offset and azimuth. Among those seismic attributes, we can notice that the seismic amplitudes and the seismic dominant frequency have the most obvious anisotropy. We apply the ellipsoid fitting to the whole seismic data gathered and obtain the azimuth of the long axis of fitted anisotropy ellipsoid. Figure A is the predicted azimuth from RMS seismic amplitude. Figure B is the predicted azimuth using seismic maximum amplitudes. Figure C is the predicted azimuth using seismic amplitudes. Figure D is the predicted azimuth using seismic dominant frequency. Figure E is the predicted azimuth using seismic instantaneous attributes. We can notice that there is an obvious changes among those predicted azimuths. The question is, which one is the most reliable one? In this research, we determine the most reliable one by calibrating the predicted azimuth from seismic data with benchmark azimuth producing using microseismic data. In this slide, I showed the histogram of predicted azimuth and the benchmark azimuth. The blue histogram is azimuth of maximum in-situ horizontal stress computed using microseismic data. The red histogram is the azimuth of anisotropy computed using different seismic attributes. Note that we have obvious differences difference between the predicted azimuths of anisotropy that are computed from seismic attributes. By comparing the distribution of the histogram, we can say that seismic dominant frequency has the best correlation with the benchmark azimuth that is computed with using microseismic data. To better say which attributes is the best attributes, we cross-plot the benchmark azimuth with predicted azimuth of anisotropy. In these slides, the horizontal axis is the benchmark azimuth that is computed using microseismic data. The vertical axis is the predicted azimuth using different seismic attributes. It is very obvious that the predicted azimuth using dominant seismic frequency has the best correlation with the benchmark azimuth computed using microseismic data. Based on the analysis, we obtain the following conclusions. In this research, we conducted a comprehensive correlation between the estimated azimuth computed from seismic parameters with benchmark azimuth computed using microseismic ruptures. The estimated azimuth computed from seismic attributes is based on the seismic attributes variation with offset and the azimuth. The statistical analysis shows that the seismic dominant frequency can be used to predict the azimuth of maximum in-situ horizontal stress in our seismic survey. At the same time, we mustn't point out that the chosen best attributes is case by case. In our case, the seismic dominant frequency works very well, but in another case, maybe seismic amplitudes works better. However, the workflow developed in this study should work for other seismic surveys. This is the end of my presentation. Now I'm ready to take any questions not related with my presentation. Thank you.